Okay, so here I wanted to talk about solving recurrences. These are recurrences with double roots. So what happens when the method that we used last time results in a double root? So for example, if our recurrence is an equals 6 times an minus 1 minus 9 times an minus 2, what's the characteristic polynomial? Well, it's going to be r squared minus 6r plus 9 equals 0. And by the way, if this 9 here were a 0, say we didn't have a term here, we just had an equals 6 times an minus 1, then this 9 would become a 0. So don't get scared off if you only see an equals something times an minus 1. Now, here's our characteristic polynomial. Notice that it factors. It becomes r minus 3 squared equals 0. And whenever you have a polynomial of the form r minus something squared equals 0, it means that you have a double root. So if you were to use the quadratic formula, you'd see that r1 equals 3 and r2 also equals 3. So remember last time we said that these two roots had to be distinct. Here they're not. There's one, slight twist. It's simple. This time the closed form will be alpha times r1 to the n plus beta times n times r2 to the n. So it's just like last time, except we're multiplying by this n here. And let me give you initial conditions. a0 equals 1 and a1 equals 6. So we have to still solve for alpha and beta. So a0 equals 1, that means 1 equals alpha times 1 plus beta times 0 times 1. So this implies that alpha equals 1. And then we have 6 equals alpha times r1 to the n, that's 3, plus beta times 1 times r2 to the n, again that's 3. So we have 6 equals 3 alpha plus 3 beta. And we said that alpha equals 1, so we have 6 equals 3 plus 3 beta. And this implies beta also equals 1. So our final closed form, we have alpha and beta equals 1, is 3 to the n plus, so alpha times 3 to the n plus beta, which is 1, times n, so n times 3 to the n. So this is our closed form for our recurrence, 3 to the n plus n times 3 to the n. Now more generally, these are called linear recurrences. So if we had a recurrence of the form an equals an minus 1 plus 10 an minus 2 minus 3 an minus 3, we would write down a characteristic polynomial of the form r cubed minus r squared minus 10r plus 4 plus 3, sorry, this is the 3 here, equals 0. And we would have to solve for roots of this cubic polynomial. And so on and so forth. As you get more complicated recurrences, these are called linear recurrences. And in fact, they're also called homogeneous linear recurrences because there's a sort of a plus 0 sitting at the end. Then, you have to solve more complicated, you have to solve for roots of more complicated characteristic polynomials. One thing that we haven't talked about how to solve, and hopefully we'll get to this in class, is what if you have a recurrence of the form an equals 3 times an minus 1 plus 2n. Right, previously we had recurrences of the form an equals 3 times an minus 1 plus 2 times an minus 2. Here I'm just adding 2n. So this is called a linear recurrence because none of these terms are squared here. So if an minus 1 were squared, then it wouldn't be a linear recurrence. But this is a linear recurrence. All the terms, none of the terms are squared or cubed. They're all raised to the 1 power. But we have this 2n sitting on here, so this makes it non-homogeneous. So this recurrence is homogeneous because it's just has a plus 0 sitting out here. It's an equals some constant times an minus 1 plus some constant times an minus 2. It's a linear homogeneous recurrence. This recurrence is linear. It's an equals something times an minus 1, but it's non-homogeneous because there's this weird 2n kind of sitting out here. We haven't talked about how to solve these, but it turns out that the first step will be to look at the homogeneous part of this recurrence, which is just an equals 3 times an minus 1. So just sort of ignore this 2n, solve this, and then handle this 2n case separately. So hopefully we'll go over this in class, but I just wanted to warn you that you do have to be careful when you see recurrences that have a strange term floating out here. The only types of recurrences that we really know how to solve right now are of the form an equals c1 times an minus 1 plus c2 times an minus 2. Again, this is a linear homogeneous recurrence.